Now we're going to look at calculation of equilibrium conditions for a system at constant temperature and constant volume. To begin this process, we start by writing down the time-dependent differential forms of the energy and entropy balance equations. So dE dt equals q dot minus p dV dt for the heat flow and work terms on this equation. ds dt equals q dot over t plus s gen dot. So we start off with the problem right away, constant temperature, constant volume. So what we can do is write constant V gives us dV dt equals 0. We can substitute this into the equations above, and we end up with the following: dE dt equals q dot ds dt equals q dot over t plus s gen dot. Now we can substitute in for q in this equation here with the dE dt term. And then I'm going to automatically move it to the other side and multiply through by the temperature to end up with the following equation. ds dt minus t ds dt minus dE dt equals t times s gen dot. Now multiplying through by minus 1, we get the following: dE dt minus t ds dt, which equals minus t times s gen. Temperature is constant is the other condition in this problem that we're trying to solve. And so what we can do in this example is now use that and incorporate things into the same derivative. So this is equal to d in brackets e minus ts dt. You can prove to yourself this is the case by just taking the derivative of this with respect to time, and the temperature term will, of course, will go to 0 when you do the product rule, equals minus t times s gen. So what is E minus Ts? E minus Ts is the Legendre transform of energy with respect to the variable entropy, which gives us the Helmholtz free energy. So this is defined as A, the Helmholtz free energy. So what we have now is that dA dt equals minus t times s gen. Well, how does this help us solve the problem? Temperature, thermodynamic temperature, degrees Kelvin, is always greater than or equal to 0. S gen, by definition, second law of thermodynamics, is going to be greater than or equal to 0. So then dA dt equals minus a positive number times a positive number, or we have dA dt is less than or equal to 0 for all time. Now finally, when the system reaches equilibrium, S gen will be equal to 0, and so then you'll have at equilibrium dA dt equals 0. What we have is a system that evolves to equilibrium monotonically decreasing to some level at which A is minimized for a system at constant temperature and volume.